All right, guys, welcome to lesson 10.3 today. Properties of logarithms, and there's a lot of them. I'll be honest, there's a few of them, and they're not very difficult. But if you know your properties of exponents, obviously you should know your properties of logarithms. They should be pretty easy. But they're needed for solving logarithmic equations. And these properties, what we use these properties for, are expanding logarithms, taking one log with a really gross insides and turn it into a whole bunch of logs that are added and subtracted together with really simple insides, or we condense where we have a whole bunch of little simple ones that we condense into one log. Yeah, and you'll see, it sounds kind of confusing, but it's not too bad. So, like I said, today's Wednesday, the 17th. As soon as we're through this lesson, you should be completing 10.3, trying your own. Make sure you know how to condense logs. Because tomorrow, Thursday, we're going to start solving logarithmic and exponential equations. And, it's a big deal. And you won't be able to do the whole 10.4 tomorrow, but you'll be able to get 1 through 5 and 8 done, and we'll save the rest of that assignment for next Monday. Okay, so as we're moving along here, I do have for you a kind of goofy-looking paper here. So why don't you try this warm-up that you have on your sheet. And number 3, you are trying to solve that 6 to the x equals 82, okay? And I will be right back. I'm going to clean this up and see why this is so jacked up. Okay, well, I got this back here. And when we're going to estimate this logarithm to the nearest 10, okay, what we're actually going to do is we're going to kind of picture a number line on here, okay? And what we really want to do is we want to find out, well, this is a log base 3 of 76. And this number 76 falls between 3 to the third, which is 27, and 3 to the fourth, which is 81. So I know down here I'm at 3 for a log base 3 of 27, and I know over here I'm going to be at like 4, and that reflects a log base 4 of 81. Well, where does 76 fall in there? Well, logically thinking, well, between 3 and 4 would be 3.5. So I would expect this to be a log base 3 of what? Well, what number is between 27 and 81? Well, that would be 54. And I can see 76 is to the right. It's between 54 and 81, but exactly where? So if I went in the middle of that, well, I know the middle of 3.5 and 4, that's going to be like 3.75. And I would expect that to be a log base 3 of what's in the middle of 54 and 81. Well, between that would be like 67.5. And I know 76 is between 67.5 and 81. Well, is it going to be 3.8 or 3.9? So the last thing I would probably do is I would say, well, what's between 3.75 and 4? That would be like 3.875, and I would expect that to be a log base 3 of, well, what number is between 67.5 and 81? Maybe 74.25, and 76 is still to the right of 74.25, so if I estimate it to the nearest 10, obviously, this is going to have to round up, and I'm going to have to say this is going to be about 3.9 with the technique of estimating I just used. And that's how we would estimate that little bugger, okay? Well, from here, the change of base formula allows you to calculate an exact value for this. And I'm going to move this over a second. I got it written there, but that's okay. So what the change of base formula allows you to calculate an exact value for logs that are not base 10. What is entered into the scientific calculator for a log base 3 of 76? Well, one way you can do it is you can use the base 10. A log base 10 of 76 divided by a log base 10 of 3. Or you might want to take Kruger's lazy route and say the natural log of 76 divided by the natural log of 3, and both of those are going to give the exact same answer, which is approximately 3.942. So our estimated 3.9 was pretty close. Okay, rewrite the following equation in the other form to solve? Well, bottom line, we look at this. 6 to what power is 82? Well, 82 is not 6 to an integer power. So what we do is we rewrite that as a logarithm. A log base 6 to 82 equals x. And then from there, we use our change of base formula to go at our calculator. Take the log base 10 to 82 divided by the log base 6, or log base 10 of 6, and it equals 6.4. Again, you could have taken, and I should have approximately equal to, you could have taken ln 82 divided by ln 6. It doesn't matter which way you go. All right. Now this very last one, okay, we worked last chapter with continuous growth. Can you solve this algebraically now? Well, Bolivia's population was 10.5 million in 2010, so that means t equals 0 at 2010. It has grown continuously at a rate of 1.6% each year. When will the population reach 20,000? Well, remember, this is bringing us to our n of t equals our n sub naught, our beginning value, times e to the r times t power. And that's what we're just doing. And so we're solving this equation. We know our initial population is 10.5. That's our n sub naught. We know our rate, our r, is 1.6, but as a decimal is 0.016 times t. When will it actually equal 20? Well, you don't need to graph this in decimals anymore, because now, hopefully, you know, we've kind of learned this. Well, we can say 20 divided by 10.5, that's going to equal e to the 0.016t, right? I'm just going to divide both sides by that 10.5. Now I'm kind of stuck. See, I have my exponential alone, and now I need to rewrite this thing to get at my exponent. So what I'm going to do is, because that's a base e exponential, that's going to be a base e natural log. And remember, logs equal exponents, 0.016t. And what's in it is the other side, 20 divided by 10.5. And because it's a base e, okay, remember, we don't have to write that thing. You're never going to see it written. And then in the end, as you're starting to move along with your calculator, if you type this into your calculator, because you can get that in there, and it's like approximately, and I'm not holding a lot of decimals, but it's 0.6443 equals about 0.016t. So t is going to approximately be equal. I got to divide everything here by 0.016 now, and it's going to be approximately equal to 40.272. Well, that's t. Well, remember, that's years past. Years past what? Years past 2010. So if I add 40 to that, it's going to be during year 2050 is when the population is going to reach 20 million, okay? So that's where we're at. So the next thing we're going to be cruising along here is exponential form. I got to hit pause here a second. I will be right back. Okay, I just have this slide here just to remind you the difference between exponential form and logarithmic form. Remember, exponential form is a base. It's some number raised to an exponent equals some result. Sometimes it's called an argument over there rather than result. Well, in exponential form, that's the log base. The base of the log is the same as the base of the exponential function. Remember, logs, they equal exponents, so the result is inside. Bottom line, you guys need to have the green light. You need to be able to fluently go back and forth from exponential form to logarithmic form to be able to solve any of these exponential equations or logarithmic equations tomorrow. You need to be able to bebop back and forth. And also, please remember, the base in the exponential form as well as the base in the logarithmic form, that is always a positive number, and it can never equal 0 or it cannot equal 1. Just remember that, okay? So what we're going to be doing is we're cruising through here. There's a pile of properties of powers, okay? Exponential, what do they look like in exponential? What do they look like as a logarithmic property? Well, the zero property of powers. Well, if you remember that, That is anything to the power of 0 equals 1, okay? Symbolically, that is b, any base, to the power of 0 equals 1. And an example, you can pop that off really easy. 3 to the 0 equals 1. Now, just remember, anything except 0 to the 0 is not 1. Okay, you won't run into that for a long time, but it's not 1. All right, well, what do these look like? Well, think about this. Symbolic, b to the 0 equals 1. Well, if I change the form of that, that's going to be a log base b of 1 equals 0. And what does that mean? Well, bottom line, the log, any log of 1 equals 0. That's what our 0 property of logarithms is. In an example, okay, b can be 3. That b, that b right there, that guy, it can be anything as long as it's positive and it's not 1 or 0. It can be anything. And if there's a 1 inside there, it equals 0. Okay? So we're going to move along now. Base raised to the first power. Well, that really is pretty obvious here. Anything to the power of 1 equals itself. That's the verbal explanation of that. Symbolically, well, that's b to the 1. B to the first power equals b. In an example, all I got to do is put a number in there for b. Okay? B cannot be a negative number, nor can it be 1 or 0, but 4 to the first power equals 4. Well, if you think here and you rewrite this, base raised to the first power, logarithms with the same base and argument, well, that's what it looks like over here. A logarithm with the same base, and the same argument, or result as we called it before. Anytime those are the same, that logarithm is going to equal 1. It's a very special property of a log. Whenever the base and argument are the same, it equals 1. Example, well, there's an infinite number. I just put a log base 2 of 2 equals 1. Why? And that's because, if you ask why, well, you change the form. That's because 2 to the first power equals 2. Okay? So these are two properties, of very important properties of logarithms. And if you notice, they are also the two properties we use to graph our logarithms, right? We said we're putting in a 1, and we're always getting out a 0, and we're going to put in the base, and we always get out a 1 whenever we graph our logarithms. Well, let's keep on moving here, because now we have the product rule of powers. Oh, what does that mean? Well, to multiply common bases, you add the exponents. Well, what does that mean? B to the m times b to the n equals b to the m plus n. If they are the same bases, you add the exponents. Example, right there, 3 to the third times 3 to the fourth, well, that equals 3 to the seventh power, because I add them. Well, what is the product rule of logarithms? Well, okay, think about this. Logarithms equal exponents. So if I'm adding exponents in the product rule, over here, I must be adding logarithms, okay? The log of a product equals the sum of the logs. They're kind of going backwards. What does that mean? Well, that means that if I have a product inside my argument or inside my result of my log, it equals the sum of the logs. Multiplication in logarithms splits up to addition because I add exponents, and because my exponents get added, logs equal exponents. You can kind of call them an exponent if you want because they equal them. An example, well, here we go. A log base b of 34. How does that turn into a log base b of 2 plus a log base b of 14? Well, the reason that can happen is because 34 is 2 times 17. Okay, I can split that apart to 2 times 17, and it's the log of the first one plus the log of the second one. Well, quotient rule of powers. Well, I don't know if you remember your quotient rule of powers, but when you do the quotient rules, okay, to divide common bases, we subtract exponents. The top exponent minus the bottom exponent. Symbolically, b to the m divided by b to the n equals b to the m minus n. An example, boom. See, I remember when I used to teach this, I'd always say, hey, where are there more 5s? There's more 5s in the top. How many more 2? Realistically, you're taking 5 minus 3 to get that 2. Well, how does this work for the quotient rule of logarithms, okay? Well, to divide common bases, if I'm dividing exponents, I'm subtracting exponents. So, if I'm dividing an argument, I'm subtracting logarithms, okay? So the log of a quotient, here is a quotient, it's a fraction. The log of a quotient equals the difference, subtractions of the log. The top log minus the bottom log, okay? An example, log base b of 5/7. 5/7, we don't usually put many decimals inside of our log if we don't have to. We can rewrite it as a log base b of 5 minus a log base b of 7, okay? Power to a power rule. I don't know if you remember, what is x to the third to the fourth? Yeah, to the 12, because, what did I just do? I went there. Because to simplify a power of a power, you multiply the exponents. What are you talking about? B to the m raised to the n is b to the m times n. Okay, well, that's 2 to the third raised to the fifth. That's the same as 2 to the 15th because I have 5, 2 to the thirds. So I have to add 2 to the third 5 times. And 3 times 5 is 15. Power rule for logarithms. Well, it's a little bit different. Okay, see, here I'm multiplying my exponents. So I take the log of a power equals the exponent times the log. So logs are exponents. So basically what happens is that exponent inside the log, okay, that exponent inside the log can power down right in front of the log and multiply it. So it's an exponent times an exponent. Really kind of thinking. And an example, log base 5, 2 to the third. Okay, well, it's just simplifying the log. We got really good at this when I was in school because our calculators wouldn't do these. We had to go to logarithm tables, okay? And they weren't fun. And what we're going to do, we're going to use all these properties, okay? So what we have here, the first ones we're going to do here, just so you know, is we are going to expand. What does expand mean? Expand means we are starting with one logarithm, okay, with, come on, baby. We start with one logarithm with multiple things inside of it. And what we are going to do is we are going to expand it into multiple logarithms with single things in each one, like that, okay? And just to give you a rule of thumb, I am just going to say, when you are expanding logs, if there is a quotient, do that number 1, do that first. And then like number 2, if there's a quotient, you would do that first. But I don't have a quotient here. I do have a product, so I'm going to do my product number 2 when I'm expanding. Well, what does that mean? Well, log base 6 of 4 equals, a log base 4 of 6x to the 5th, that equals a log base 4 of 6. And this multiplication right here means plus a log base 4 of x to the 5th, okay? And so I expand all my multiplication into addition. And the very last thing I want to do is I want to use my power property here at the end, which means this one doesn't have an exponent on it, so I'm just going to call this a log base 4 of 6 plus, this is going to be 5 times a log base 4 of x. And when you expand logarithms, you expand from ugly into very simple logarithms in each one, and I usually put parentheses in there, okay? So why don't you try the next 2 quick, and I'll be right back. Okay, like I said above there, what we're going to do is we're going to do this division first because, see, that fraction, so that's a log base 7 of 3y to the 4th minus a log base 7 of x to the 3rd. The next thing I'm going to do is I'm going to take care of this product right here, and that's going to give me a log base 7 of 3 plus a log base 7 of y to the 4th, and I had no product over here, so I'm just leaving that x cubed alone. The last thing I do, the very last thing I ever do, is my power rule for logarithms, which means this one doesn't, the first one doesn't have power, so that's log base 7 of 3, plus this is going to be 4 times a log base 7 of y, and this last one's going to be 3 times a log base 7 of x. So when I expand it, okay, notice I'm taking one log with a very yucky inside and I'm expanding it into multiple logs with very simple insides. That is called expanding a log, okay? And if I came to the next one, well, this is the ln. Well, don't worry, that's just a log base e, so the properties work the same way. So because I see there's two multiplications, I'm going to have an ln of 3 plus an ln of x plus an ln of y to the third. And then, because I didn't have division, I took care of my multiplication. The last thing I'm going to do is my powers. The first one doesn't have a power. The second one doesn't have a power. But the third one, yeah, it's got a power right there. And that expands that log, okay? That's expanding logs. Expanding logs go from ugly to simple, okay? Well, when I come to this next package here, make sure you change this in yours, okay? Get rid of expand and replace that with condense. Here we're going to condense logs, okay? And I condense logs in a different order. I'm very process orientated when I do these. When I condense logs, the first thing I do is I power my logs up, okay? And then I do this from left to right, following the order of operations. This is just my way to do it. That's what I do. What are you talking about? Well, if I'm going to condense this first one, okay, notice I do have one there. That's going to be a log base 2 of 10 plus a log base 2 of x to the third power. Okay, now I'm adding. So I get rid of all of these all of these powers. I throw that power back up, and I'm moving it back. When I condense, I'm taking simple logs, and I'm writing them into an ugly one. And then addition here, well, that addition came from multiplying those two things together. So this is going to equal a log base 2 of technically 10 times x to the third. Well, you know I don't need that dot for times. It's the log base 2 of 10x to the third. And when you condense, you are done when you have one log left, okay? Number 5. First thing I'm going to do is I'm going to power these up, okay? So I'm going to look at this as a log. Ooh, these must be log 10, base 10s because they're naked bases. But that's going to be 12 to the 4th minus, that's going to be a log base 2 to the third. Now I'm going to do subtraction. And if you notice that subtraction, I'm dividing my logs. It's the first one divided by the second one. So this is actually going to equal a log base 10 of 12 to the 4th divided by 2 to the third. And that looks pretty gross. 12 to the 4th is a pretty good size number. I really don't want to do that. So I'm going to look at this as a log, and I'm going to look at that as 12. I'm going to think of that as 6 to the 4th times 2 to the 4th divided by 2 to the third. Okay? And I can see these get rid of 3 of those, so there's only one of those left. So this is actually going to equal a log of 2 times 6 to the 4th. Boom. And it's kind of simplified there, right? And the very last one. Well, now, following the order of operations, notice I do have powers here, but I have parentheses. So I'm going to say this is a 3. This is going to be a log of the first one divided by the second one, plus this is a log of the first one divided by the second one. Okay? Well, now I do have this power I'm going to kick up. So what that's going to give me, that's going to give me a log of, well, I know 3 to the third is 27, and I know x to the third is x to the third, plus ln x over 9. Well, what does this equal? Well, now these are multiplied. That means it's 1 log, and I'm going to take these 2, and I'm going to multiply these 2, and not only am I going to multiply them, I'm going to reduce them, and see that's a squared. That goes away. That's going to be a 3. So this is actually going to equal the natural log of 3 over x squared when it's condensed, okay? And we need to be able to condense logs to solve logs, okay? You'll learn that tomorrow. Very last one, okay? We are going to suppose a log base a of 5, we're going to call it m. A log base a of 3, we're going to call it n. And a log base 2, a of 2, we're going to call it p. Write an algebraic expression for each logarithm. So I need to see this number 50 as products or quotients of the numbers 5, 3, and 2. So I'm going to say, hey, this is a log base A, and I can get 50 by taking 5 squared times 2, can't I? Because that's 25 times 2 is 50. Oh, so this is going to give me a log base A of 5 squared plus a log base A of 2, and I can see this 2 is going to come right down here. So I'm going to say, and when I power that little guy down, that's really where I'm at now, right? So this is going to be 2, well, a log base A of 5, that was a log base A, that was 2m plus, what was a log base A of 2? A log base A of 2 was p. So why don't you go ahead and try these last two quick, and I'll give you a hint on this one. Let's call this one first a log base A. Let's rewrite that decimal maybe as 3/10. Okay? And my A's always look like 9, sorry. So why don't you go after that, do these two. I will be back with the answers in just a second. Okay, sorry for the length of this. We got a lot of stuff going on today though, but we're going to take that log base A of 3 divided by 10, and we want to take that 10, because remember, we're doing these all, we need 5s, 3s, and 2s inside here, because we're rewriting them as expressions of m, n, and p. Okay, so 10 is 2 times 5. Well, notice, that is the log base A of 3 minus, using my properties of logs, the top minus the bottom, and then it gets really sticky here, because what I'm looking at really is minus a sum when I expand here, because this multiplication breaks into a sum, so it's subtracting a sum. And when I power them all down, if I had any powers, well, it's really n minus, well, here's m plus, here's p, and I can distribute this negative, and I can say it's n minus m minus p. I'm just breaking them into those insides. They're all the same base. Okay, I'm just breaking all the insides into the numbers 5, 3, and 2 to make these done. Well, this log base A of 1 over 27, well, 1 over 27, I like to see that as 3 to the negative 3. And if I use my property of a log and I bring that power down, I bring this guy down here, well, now I'm right here. Okay, well, that's negative 3 times a log base A of 3 was n, so that's negative 3n. Okay, and from there, well, that's it. 10.3, trying your own. Go at it. Please ask questions if you got them, and we'll talk to you tomorrow. Good night.